In this video, we introduce two tests that we sometimes apply to check convergence, divergence of infinite series. They're called comparison tests. Now, first one is called term-wise comparison test, or TCT. The theorem, or the result, or the test says, suppose sigma a sub n and sigma b sub n are both positive series, meaning all the guys involved in the sum are positive, or called positive term series. Now, one case, if a sub n is less than or equal to b sub n for each n, so we're comparing term by term. That's why we call this as a term-wise comparison. If this is true and sigma bn converges, we conclude sigma an converges too. Second case is, if again we compare term by term, sigma an is greater than or equal to sigma bn for each every n, and if we know sigma bn diverges, then our conclusion is, it should be sigma an diverges too. So basically what this says is, giving a series to check out if we can come up with a bn, those conditions satisfied, we can say sigma n converges. Those conditions satisfied, we can say sigma bn diverges. So we need to find the sigma bn in practice. Now, let me briefly kind of explain why this is true. Roughly speaking, say case 1. This is a given. This is the one we're going to find. And I'll show you how to find this guy. So if we find such sigma bn and such that the inequality is true, it means these ans are smaller than bn, then it's kind of clear that if you add them up, the sum will be less than or equal to that, because each every one is less than or equal to, each every an is less than or equal to bn. So the sum, we can kind of imagine this would be true. With this condition, we know it's a finite number because infinite series converges. So that's a finite number. Therefore, this would be a finite number. That's just like a rough estimate. Rigorous proof involves some special results from math analysis. So we're not getting into that. Similarly, case 2 says, given sigma n, we find the sigma bn so that we have this kind of comparison. Well, it means each every one here is greater than the respective term in this sum. Then we can tell this got to be true. Now that condition says this one diverges. So it means it's infinity. So this would be infinity. Therefore, sigma a sub n diverges too. That's how we kind of understand intuitively why those results make sense. This is not rigorous proof. Well, we don't worry about proof. So this is our term-wise comparison test. Now we're focused on how to apply this test to check series for convergence, divergence. Now, there are two basically results involved here. One we use to check convergence of a series, other we use to check divergence of a series. This is the one that's given. We're given this. From the result, we can see if we want to show a series converges, we have to find a larger series with greater numbers. If we want to show series diverges, we have to find the sigma Bn with Bn's smaller than An. So practically, to apply the test, we need to know, we have to have some idea or at least some estimate whether the series will converge or diverge. For example, if we suspect it's going to converge, then we'll try to find a bigger Bn. If we tend to believe the series will diverge, we better find a smaller series, sort of series containing smaller numbers. And of course, this would have to diverge. Then we can conclude sigma n will actually diverge. So anyway, this is a term-wise comparison test. Now you know, in order to actually apply this test, we have to have some idea to know which way we're going to go. Either we're going to try this, we're going to try this. So it's important to apply this test to be able to roughly estimate the series for convergence divergence first. Now, how do we estimate the series? Usually what we do is to drop low order terms involved on the top and the bottom to come up with a series we know, like a geometric series, like in most cases P series, because those series are obvious. By kind of simplifying the series first, we just get some idea before we actually try to take this route or this route. So we need to know to estimate, then apply the test to actually show the series will converge or will diverge. Alright, let's see examples. Sigma 3n squared plus n over n to the 4th plus square root n. Yeah, it doesn't matter where n start out, say n start from 1 to infinity. For convergence divergence, it's those guys, when n is very large, that matter. So doesn't matter what n start out with. Alright, we'll try to apply term-wise comparison test to check this one out. Well, so this is a sigma an. This is our an. Now you see, there are two ways. One, we would try to find the larger bn's, sigma bn converges, and we conclude sigma n will converge. Other ways to try to find the smaller bn and sigma bn diverges, and then we can say sigma n diverges. So which way? So this is why we have to have some idea, guess, whether the series will converge or diverge, and then we decide which way to go. Okay, then how do we estimate this guy? Well, look at the series itself. We drop a low order term. Now, if we drop a low order term, basically we are just checking the terms when n is very, very large. When n is very, very large, for example, the top, when n is very large, the n can be dropped, can be ignored compared to 3n squared, because n is so large. similar to the bottom, we can drop square root n. This is a lower order term. It's very, very small compared to n to the 4th power. Right, this is the basic idea. So we drop the lower order term n from the top. We drop lower order term square root n from the bottom. Now, this is almost like the simplified version of the series when n is very, very large. As a matter of fact, those two would behave similarly when n is very, very large. Again, I have to emphasize it's for n very, very large. But this would, at least this is simpler version, is not the same exact series as this one. However, this will help us have some idea what this series is going to be like, whether it's going to converge or diverge. This will tell us what we need to know. Okay, so the simplified version now is like a sigma n squared n to the 4th cancel out to 3 over n squared. Well, 3 is constant, we can always move out. So effectively, this is like a p series. P equal to 2 converges. So the simplified version of that converges. Then we think this series will probably converge. Now we get the idea. It will probably converge, then we probably should be looking for larger numbers as Bn. Okay, so we decide to try this because of our estimate. So try this out. Well, this is the algebra now. This is the interesting part. Okay, we're not giving Bn, we're only giving An. So this is how we come up with the Bn. Larger terms, but not so large, because the sigma Bn in this case better converge for us to actually show sigma An converges. So let's see how we come up with the Bn here. Well, there are two things involved. One, we want to have a larger term or fraction as Bn. Another, the sigma Bn better converge. So we got to be able to know for sure the sigma Bn will converge because of whatever result we already know. So it's not going to be just to estimate anymore. Oh, it will probably converge. Oh, it will probably diverge. So we have to draw a conclusion based on knowing results, knowing theory. Well, let's face it. We know two series offhand. P series. There's a P series test. What's P series test? Sigma 1 over n, the pth power. We know offhand. It converges. If it's more than 1, it diverges. So less than 1. That's P series test. And there's a geometric series test. And it says basically a times r to the nth power. Now, a and r are constants. This is going to converge if absolute r is less than 1. It's going to diverge if absolute r is greater than or equal to 1. So those are the two known simple tests we often use to claim that whether the sigma Bn will converge or will diverge. Alright. Well, so how do we get to the Bn? Hopefully it's going to become a P series or geometric series, so we can tell. Any other series, we cannot tell. Whether we want to come up with a p-series or geometric series, the key is to somehow come up with one term on the top, one term on the bottom. Cannot have multiple terms. Okay, so to come up with one term, there are a few things we can do. One, if it's okay, we drop a term. In case we cannot drop a term, we may want to replace, for example, say the n by another n squared term, if that's allowed. If this, say, if we can replace this by n squared, then those two n squared terms can be combined into single n squared term, one term. So it's very important, no matter what you do, you have to have a one term on the top, one term on the bottom. This will make it possible for us to come up with a p-series or geometric series. Always like that. There are two ways to reduce the number of terms. Drop a term or replace the terms you can combine. Alright, now we'll see the expressions we have and the thing we can do in order to achieve the goal of having one term on the top, one term on the bottom. And before we do it, there's one more thing I want to stress. You never touch the higher order term, whether on top or on bottom. Like the square term, you're not going to touch that. Into the fourth power term, you're not going to touch that. Remember that. Okay. So, let's see. In this option, we want to basically make this thing bigger as our Bn. So now, how do you make a fraction bigger? Well, we can make denominator smaller, the fraction will be bigger. We can make the numerator bigger, the fraction will be bigger. Okay, let's start with the top. So we have 3n squared plus n. I want to make the fraction bigger, so we're going to make the top bigger. That would work, right? That's okay. Now remember this thing we talk about. Our ultimate goal is to have a one term on the top, of course on the bottom too. In order to have one term, I want to make it bigger. What I can do is to replace the n by, well, n squared. N squared is greater than n because n are integers, so 1, 2, 3, 4, 5, 6. It's okay. Algebraically, this is okay. And then you can imagine later on those two terms can be combined into single term. That's what we want. Now bottom, n to the fourth plus square root of n. We want to get one term on the bottom. And at the same time, when we do that, we make sure it's going to be smaller. Therefore, the fraction will be bigger overall. So, well, in this case, look, we can just drop this guy because it's a positive term. So drop it. Now we have one term. Okay, so you see this is now 4 to the nth power, n to the fourth power. And simplify, it's a 4 over n squared, right? Like a p-series. This is our Bn, because we know offhand by using some test, p-series test, we'll claim sigma Bn converges. Alright, so we actually in this problem so far try two things. One, we replace the top term by something else. Two, we drop this guy to achieve our goal of having one term on the bottom and this eventually one term on the top. So we know what's going to happen to this one. So let's actually say sigma Bn we obtain this way is 4 over n squared, and this converges because of our p-series test. P equal to 2 greater than 1, p-series test. Now sigma an converges. Well, this is based on our turn-wise comparison test, which establishes inequality an less than equal to bn. We claim, so this is the one assumption. Another assumption, 2, this thing converges because of the p-series test. So the two conditions, sigma n less than equal to bn, sigma bn converges. We check it out, that's true. Therefore, we can claim sigma an converges. Alright, let's see another example. So we have sigma n plus 2 to the n over n plus 3 to the n, and start from whatever number, say 1 to infinity. Let's check this converges, diverges. We are going to try to apply the term-wise comparison test again. Well, as you saw in the first example, to decide which way to go, we need to estimate first. The same way, drop n from the top, drop n from the bottom, because those are lower order terms. N is lower order compared to exponential, n is lower order compared to exponential. So the simplified version of that is basically a geometric series. Now this is like R. It's less than 1, so we know it converges. Notice, we're just estimating so far. This is not our Bn. Now, from our estimate, we know this will probably converge. So we start to let's copy that down. Sorry, it's n plus 2 to n. Try to come up with the inequality we would want again, because we think this will probably converge. Let's try to find a larger series called sigma bn that also converges. Alright, here again, 2 turns on the top, 2 turns on the bottom. We try to get 1 turn. To make a fraction bigger, we're going to make the top bigger. So it's gonna actually same treatment. We'll replace the n by 2 to the n. Now 2 to the n is higher order than n, so never touch this top, never touch this on the bottom. Just do whatever you can with the lower order terms. And later on, those two can be combined into a single one. The bottom, well, we want to make the fraction bigger, so you can just make the denominator smaller. That will ensure the new fraction will be bigger. And this, now you see the top is like a 2 of 2 to n, just combine those two over 3 to n, or like a 2 times 2 over 3 to the nth power. This is our Bn. and we know this would give us geometric series and converging one too, because r is less than 1. You can see this is our BN. Now when we were estimating, we got that's not the actual BN we're using. So again, we say sigma BN now is sigma 2 times 2 over 3 to the n power 1 to infinity. This converges geometric series. Geometric series. R is 2 over 3 less than 1. That's how we know this converges offhand. Therefore, we conclude sigma AN converges, because we showed that sigma AN term wisely, each A sub n is less than or equal to each corresponding B sub n, and sigma P sub n converges. So this converges. This is our term-wise comparison test. Okay, two conditions are satisfied. Sigma n less than sigma bn, sigma bn converges, so the converge. Let's see one more example involving this test. Alright, say n start from whatever 5. So I don't want this to be negative. Start from 5. This is going to be positive, starting from the first term. Anyway, so I'm going to estimate. When n is very large, I can drop the 3 from the top. When n is very large, I can drop the 2n, because this is the first power. This is like a 1.5, so this is a higher order. I still have 3 over 2. And this is going to give me a diverging series. P series, we know P is less than 1, right? So it's going to diverge. Now, since this is going to diverge, we're going to this time try inequality this way. We believe sigma n will diverge, so we're going to try to find a smaller series, sigma bn, with each bn less than or equal to an, and hopefully this will diverge too. Alright, so through this example, I just want to show you how we establish the reverse kind of inequality, right? So this fraction, I want to make this fraction smaller. How to make a fraction smaller? I can drop term, I can replace term. No matter what, I better have one term on top and the bottom. That would make it possible to hopefully get a P series. Okay, so with the fraction, how do we make a fraction smaller? We can make top smaller, bottom bigger. Well, let's start with the top. I can drop a 3. If I drop a 3, the top becomes smaller, fraction will become smaller. So that's easy enough. The bottom. What can we do? There are two terms. Well, basically, what are we going to do with this guy? We never touched the higher order term anyway. So what are we going to do with this guy? Now, what are we trying to get? We're trying to get bigger denominator, so the fraction is smaller. Bigger denominator in this case is actually too trivial. We drop just 2n. If we drop 2n, it's going to be bigger because it's negative. We don't subtract anything from that anymore, so it's bigger. So we just drop. It's too simple, too boring. Actually, let me change the problem a little bit because I made up this problem. Now let us change it so it's more interesting. Basically, I'll be able to show you more trick to achieve our goal. Alright, let's say it's plus on the bottom. That's not going to affect how we estimate with stir drop loader time. That remains to be the same. Anyway, so now with the plus on the bottom, again, what did I want to do? I want to make the bottom bigger, right? I want to make the bottom bigger, and then I cannot drop the 2n anymore this time. Well, it's a trick we applied before. I can do this. I can replace the 2n by n to 3/2 power, because when n is large, this is more than that. Therefore, the sum is more than that. The bottom is bigger, top is smaller, so the fraction overall is smaller. Now, with this, I can combine the two terms on the bottom. See, with one term on the top, one term on the bottom, I can simplify. So this is like a 1/2 times 1 over into half power. That's gonna give me P series. The constant factor will not matter, you'll see. Okay, this is our Bn. So now let's check. This time, what's our sigma Bn? Sigma Bn is the half. I can pull out the half. Exactly a P series multiplied by half. But this P series diverges infinity, so multiplied by 1/2 is still infinity, still diverges. So anyway, this thing diverges because it's a P series. P equal to 1/2 less than 1. Alright, so I got the inequality A sub n always greater than or equal to B sub n, and sigma Bn diverges. Now, according to our termless comparison test, second case, An greater than or equal to Bn, sigma Bn diverges, so sigma n diverges. This is because our term-wise comparison test. Alright, so this is another example. Let's see how we try to establish the necessary inequality. Greater than or equal to or less than or equal to depends on our estimate. Actually, the thing we try to do, and how I change from minus to plus to try to show you, different thing we could do. Actually, got another idea. Let's just modify this problem a little bit. Then you can see again how, say, in minus this time 10 over, say, n squared, so minus. The difference you'll see in treating this series is here when compared to this series. Anyway, let's do another example. So I start from 2, so this way the bottom will not become 0. Oh, actually not. We want to make sure everything is positive, right? I start with 20. It's not that important. What's important is different thing we'll need to do to check convergence divergence of this series, specifically how we come up with the inequality. Alright, let's do estimate again. Won't hurt to see another example. The main thing is I want to show you something when trying to come up with the necessary inequality. Let's estimate. We'll drop lower term, that's the same. Drop the 10, drop the n from the bottom, and this is P series, actual harmonic series, diverges. Simple enough. Well, this just says we think this will diverge. This will allow us to know kind of inequality we want to establish. We want to be greater than equal to, just like this problem. So greater than equal to. Now you see the difference. How we come up with the desired, a simpler fraction. Okay, we want to have a smaller fraction. The top one, let's start with the top. Top is n minus 10. We want to have smaller fraction. Two things. One, we can make the top smaller. We can make the bottom bigger. The bottom is easy. The top is what I really want to show you through this example. How can we make the top smaller and at the same time to somehow ensure eventually there's one term at the top? Well, two things we can do. One, we drop terms sometimes. Another thing is we replace somehow a term or lower order term. We never touch the n anyway. So what can we do with the 10? We cannot drop 10, because if we drop 10, it becomes bigger. It's like we no longer subtract 10 from n, so cannot drop 10. So we need to replace 10 by something. What then? Well, in this case, I'm going to replace that by, say, 1/2 times n. Would this work? This would work. Well, when n is large, 1/2 n or n divided by 2 is greater than 10. N goes to infinity. N is 100, 1,000, million. So of course, this is greater than 10. So then the new difference, really, I'm subtracting whole a lot more from n compared to subtracting only 10 from n. So that's smaller. Now why do I have like an n here? I wanted to combine. Why do I have 1/2 here? I want to ensure when combined, I still have a positive coefficient. For example, I cannot have a 5n here. Although mathematically, n minus 5n sure is less than n minus 10. The problem is, if I have 5n here, negative 5n here, I will get the negative thing. That will ruin everything, because our a and b and should be all positive. Anyway, so 1/2 would work. You can imagine 1/4 would work. 1/3 would work, as long as it's a positive number less than 1. All right, that's new. This is a new thing I want to show you through this example. The bottom. What do we want to do? We don't want to make the bottom bigger, right? But make the bottom bigger, so it's just drop the n. Drop the n, it's bigger. Alright, that's pretty simple, obvious. Okay, the top now can be combined into single term. Bottom is single term. So I have 1/2 times, actually 1/n. That's my Bn, because I know, well, P series basically. Just like a previous example, then we actually state sigma Bn, there's 1/2 in the front, diverges P series, P equal to 1. So we got the inequality, sigma n greater than equal to sigma Bn, and sigma Bn diverges. Condition satisfied, so sigma an diverges. This is because of term-wise comparison test. So this is just another example. Now, there's another comparison test. It's called the limit comparison test. Let's see. It says again, with the two positive series with positive terms, if we compare the limit, we do the ratio an over bn, check out the limit. Suppose the limit is a positive number, finite, then we claim both sigma an and the sigma bn will converge, or both will diverge. Now what happens is this. Okay, so this is our condition. So if this is true, sigma bn and sigma an will behave the same way in terms of convergence and divergence. Why is this true? Well, let's just roughly see the proof. The proof actually is very simple. This case, it's also based on the termless comparison test too. So anyway, suppose the limit is L. That's L is some positive number. So we're saying the limit is L. Therefore, when n is large, this fraction is very close to L. Then we can definitely conclude that when n is very large, this fraction is going to be more than L over 2, because it's going to be really around L, right? So of course it's greater than L over 2, and then less than 2L. Think of this fraction. Well, it's a sequence, right? So the limit is L. Eventually, all those fractions will be close to L. That's what we mean by limit is L. Therefore, of course, all those guys will be more than L over 2 here, less than 2L up here. So all those values will, we can establish inequality. And this means an is multiply both sides by bn. So 2L times bn, L over 2 times bn. Now we do sigma. So get this is inequality. Then from our termless comparison test, say this part would say if an converges, bn will converge. If bn converges from this part, then we can tell an will converge. Similarly, if bn diverges, we use this part. Bn diverges, sigma is greater, right? So it will diverge too. If this diverges infinity, that's infinity. If an diverges, we use this part to say sigma bn will diverge. So this is basically the proof. Just organize the cases. It says as long as the limit of this ratio, we're comparing like really like the limit here. The limit is a positive number, finite positive number, then both series will converge or diverge. To apply this test, again, we're given sigma an, so we'll try to find the bn. The idea is, if we find a bn, of course we would have to know whether it would converge or diverge, right? Form the ratio. Suppose we end up with some bn's. We know it's going to converge, and to do the limit is a finite positive number, and we can say this will converge. Then we find the sigma bn is convergent, that's divergent, and then we do the limit, and that's true, then we can say this is going to diverge too. So to be able to apply this test, which is much simpler than the terminus comparison because we don't need to estimate anything. This is just the proof. We don't need to worry about it. All we need to do is to come up with the sigma BN, check the limit. So the only question is, how do we come up with sigma BN? The good news is sigma n, most of the time to come up with sigma BN, we kind of drop lower order terms in sigma n. That's all we need to do. Let's see example. So we have 1 over n minus log n, drop lower order term. This is our an. Our an is n minus log n. So we drop lower order term. Well, there's only one term at the top. There's nothing to drop. Just drop log n from the bottom. And this is RBN. Also, we know after we drop lower return, this one diverges. It's a P series, P equal to 1. Alright, so we find RBN very easily. Now form the fraction. So let's do the limit. To make sure the limit is positive finite number L. N goes to the top. Actually, it doesn't matter which one goes to the top or which one goes to the bottom. But let's just do it according to the test. Bn, this is our Bn. So evaluate the limit here. First of all, simplify. We flip the bottom, becomes n on the top. Simple algebra. Now evaluate the limit. This is an indeterminate form. We can apply L'Hopital's rule. Since n goes to infinity, we can also drop the lower order term. So if we drop lower order term, it becomes n over n. This is 1. We cross out 1. As a matter of fact, when you obtain your sigma Bn by dropping all lower order terms from the top and from the bottom, most of the time the limit of the ratio is 1. Not necessary, but it's not always true, but doesn't matter. You just you get whatever you will get. Anyway, so this is our an, this is our bn. Limit of the ratio is 1. Of course, it's positive. It's less than infinity. Therefore, according to our test, sigma n, sigma b will behave the same way, meaning either both will converge or both will diverge. But we know sigma bn diverges. So let's just copy down that. Because sigma bn diverges, then we conclude sigma an will diverge. This is the limit comparison test. So again, given a series, we try to come up with the bn, sigma bn. Most of the time, drop lower order terms. This example, drop lower order, get a divergent bn, divergent sigma bn, then form the limit and show the ratio approaches 1, which is positive finite number. Therefore, because sigma bn diverges, we can tell sigma an diverges too. Let's see one more example. So this is our AN. Okay. Here, let's try to come up with a sigma Bn. This is not to estimate. It's actually try to obtain sigma Bn. How? We drop lower order term. Drop the n from the bottom. So this half part on top, second part on the bottom. Simplify. It's 3/2. That's our Bn, sigma Bn. By the way, we know this will converge because it's more than one. Now form the fraction. So limit square n squared over n as an on top, 1 over n to 3 half power on the bottom. That's our Bn. So simple algebra, we flip this guy, n goes to infinity, n goes to infinity. How do we find the limit here? Well, actually the half power and the 3 half combine into a square on the top, and we drop lower order term from the bottom. N square cancel out. The limit is 1. See, most of the time the limit is 1 if the Bn is obtained by dropping lower order terms from the top and the bottom of An. Anyway, limit is positive finite number, and we know because sigma Bn is a p-series converges. It's p-series. P more than 1. Therefore, we conclude sigma An, that's our original given series, converges. So this is how we apply the limit comparison test to check convergence, divergence. Now from these two examples, you see, in order to apply this test, we got to be able to somehow simplify or draw terms in order to get a sigma Bn that's known to converge or to diverge. Alright, so this is the limit comparison, and this is the termwise comparison. They are different. Well, actually, the limit comparison, as I explained here, is based on the termwise comparison. It's much easier, the limit comparison test. The only problem is, if you cannot, from the examples you see, if you cannot drop lower order term to come up with a series we call sigma Bn that's known to converge or diverge, well, you won't be able to tell. You got to be able to simplify. Basically, you got to be able to drop terms. You cannot drop, cannot apply this test. We won't be able to find the sigma Bn. That's what I'm saying. Well, termwise comparison, of course, is a little different. You need to estimate. In order to estimate, most of the time, again, you need to be able to drop. You drop lower term, so hopefully you can simplify it. Given a series that's simplified enough, that's a simple enough, you cannot simplify anymore, then you would probably have trouble applying this test too. I can just offhand, I can just say you have n log n. This one, none of these comparison tests would work because it's difficult to estimate So if you want to try term-wise comparison, you would have no idea which way to go, what kind of inequality to establish in order to move forward. So you don't know whether it's going to converge, so you'll probably not try that. You don't know it's going to diverge, so you're probably not going to do this. So if you cannot drop, most of the time you cannot estimate. And for this one, the limited comparison test again would not apply, because you won't be able to, this is RAN, you will not be able to come up with a sigma BN that's clearly convergent or divergent. Cannot simplify, cannot drop, that's what I'm saying. Alright, at least for those we can estimate, we can try term-wise comparison test. For those we can simplify to a series we call the sigma BN that's clearly convergent or clearly divergent, we can try limit comparison test. Okay.